So we just have these truth tables illustrating for all possible combinations of the values of the variables, what's the value of the expression. And so here's the general form that these are put into, and you can put any statement that you want up here and then fill in the table. And so here's an example. We want to do not P or Q, or Q. And I want to do this two different ways. I'm going to make the table just the way it's written at first, but then I want to simplify that expression a little bit and see, we might make the table a little bit more easily with the simplified form of the expression. Okay. And you can organize your work in a lot of different ways. I'm going to write equations across here. Where I start, I'll just substitute in the truth values, substitute for the variables, and then simplify after that. Well, now I could start boiling it down, but let's look at what's the last operation performed here in the order of operations. The negation is just like putting a minus sign in front of a number. So the parentheses come first. We're going to get whatever this is, and then we're going to negate it. And then last of all, we're going to do this or. So it's whatever or t. Well, looking back up here, whatever or t, or t is always going to be t, right? Because only one of the two things has to be true, and here's this t, it is true. So I've got some mess or true. That's true. I don't even have to think about what this mess comes out to be. So I just say true. Now let's do this one. So now, what's inside the parentheses? False or false, right? Not T is F. So this expression here, it's false or false. So that whole inside of the parenthesis is false, because it's either false or false. Okay. So now what have we got? Not false or false. So true or false. Well, it's true, right? I mean, every statement, it's either not false or else it is false. Okay. So you can simplify them. And that's how it works. Now you might want to, like when you do algebra, you can do it horizontally, you can do it vertically, you can go off to the side and do your calculation that way. Okay. Now I want to take one other approach. So this time, and you know how when you did algebra, you can substitute numbers. You can go through and you can find all the letters, and if you know the numbers, you could put the numbers in, substitute the numbers, and then do the arithmetic. Or you can algebraically simplify the expression first and then put in the numbers. Well, same way with the truth values. Now, how do you negate a disjunction? See how those are equivalent expressions? Doesn't matter what A and B are. Not A and B means not A, or not A or B means not A and not B. So I'll apply that down here. I have when I'm doing the not A or B. So I got not P, that's P, and not Q. So I've either got Q or I've got P and not Q. Now, do you see how that's the same? Like up here, if Q is true, this is true. Also, if Q is true, this is Q, true. So it's like if Q is true, those two expressions have the same value. Okay. Well, what if, regardless of P? Okay. So what if Q is not true? The thing's still true if P is. See, if we got not Q, if Q is false, not Q is true. The whole thing depends on P then, that's all. So the way you can tell they're the same is you can make a truth table for these two expressions if you needed to, but they carry the same meaning. So I could have done algebraic simplification first and then put in the values. Now it's a little bit dangerous until you get used to it, because you can make algebra mistakes. So I think the way they had in mind for you to do it, this is your first example here, you know, the first truth table that you do. They don't have you doing the simplification first. What they're thinking is you'll just put the T and F in first, and then go with it. Okay. But then you can learn to simplify the expressions. Okay. Do we have questions up to here? Wow. I don't know, these old Western movies, it's quiet, too quiet. Okay. All right, well, I think let me look at some more of these. So, wow, they're really breaking it down, aren't they, to do their solution. I kind of did it all in one row, but look what they did. They said, well, there's a not P in here, so let's figure that out. They made their table for the not P. And they added that in here. And then they said, okay, inside the parentheses, what have we got? We got not P or Q. So they came down and they worked out that part. They say, okay, let's add that to the table. So now I got the P and Q that I started with. I got these little pieces of the expression. And they said, what's next in the order of operations? After I do the parentheses, I negate it. So they show, okay, here's where I took what's in the parentheses from this row, and I negate that. So T turned into F, and F turned into T, and so forth. So they keep making new tables, and each time they make a new table, they add in, you know, a new piece of the whole overall expression, until finally they come down to a table that's got the whole thing. And then we find out, you know, as long as either P or Q is true, either way, any of these first three, it's true. The only way it's false is if they're both false. Like I said over here, you got to have P or Q, just not both. Let's see. Are we good up to here? Okay, so, you know, do the check your progress things are really good because you don't get graded on it, and you can find out whether you understand. It'll tell you if you're right. It'll show you the answer. So I urge you to do those. So here they're going to let you make the entire table. And then in question B, you look up a particular one, a particular row in the table, given that P's true and Q's false and R's false, or Q's true and R's false. So first they have you make the whole table and then check for particular values. Does anybody want me to talk all the way through example 2, or do you feel like you can read it? Okay, let's. I'd like to get some feedback here. Let's get a yes no on the show of hands in the participants window. Should I go through example 2 in detail? Give me a yes or a no. All right, I got some yeses popping up. Okay. So, the first thing I do is I list all the possible values of P, Q, and R. Okay, so all the ways, all the combinations of true and false that you could have. So you'll start out, you'll list all the ones where P is true. You know for Q and R, there's 4 of them. There's the ones where Q is true, 2 of those, and the ones where Q is false, 2 of those. Okay. So you get these 4 different ones where P is true, and then a similar 4 different ones where P is false. And so you have 8 different combinations of truth values for P, Q, and R. All right. So, where are they getting these rows here? Well, see, they say, okay, and we got in parentheses here, do the expression in order from left to right. So we got the parentheses, the P hat Q. So they start out and they say, let's just forget about the rest of it, and let's just work out the P hat Q for all of the 8 combinations. And so if P and Q are both true, then you have P and Q true. Okay. So these 2 rows where P and Q are both true, they get true. But all the rest, if either Q is false or P is false, or both, all the rest of the rows get false. So they looked at the expression, they thought about the order of operations. They say, I'm going to do the insides of the parentheses, and I'm going to do those from left to right. So my first job is the P and Q, and then they made a column in their table to do just that part. And then they continue with the order of operations. They say, now we got to do the parentheses on the right. We have to do the not Q or not R or Q. Okay. So they got to do that. But before they can do it, they're going to need the not R. So they forget where it came from, and they take the not R or Q as an expression all to itself and say, well, the first step in doing that would be the not R. And so they make the table for not R. When R is true, they put a false. When R is false, they put a true, and they fill in that column. Okay. And they say, well, I still have to finish out doing these parentheses on the right-hand parentheses, the not R or Q. So they make a new heading in their table. They say, okay, I'm going to do the not R or the Q. Okay. And so they say, well, here we go. Here's not R. Here's Q. So we got false or true. That's true. We got true or true. That's true. But here we get false or false. It's false either way. You got false. True or false. That's true. So you go down the list. You can refer back to the, you got a table back here for just or somewhere. Way back there, okay. Oh, it's back, aha, okay, here, way up at the top. It shows you how to do the R's, so you can do T or T, T or F, F or T, F or F. Okay, so you use that table to fill in this column. And then you've got all the pieces. You got this piece, you've got that piece, and now all you need to do is to make their conjunction, their and. And so, so you look here and you say, okay, this piece is T, And this piece is T, so you've got T and T. You fill in the T. And so it goes. I'd like to ask, oh, somebody's got their hand up. Surin. Surin Rijal.
Yes, yes, sir.
Hey, what can I do for you?
This one, that's a P or Q, yeah. If in every truth table, all the pattern goes like this, same, like we have found P or Q is true, and true P is true or Q is true and R is false, then it's true again, yeah.
Let me write, because I'm afraid I'm going to say yeah when I didn't understand what you were saying, and then you got the wrong idea. Okay.
Okay.
Yeah. So tell me one more time. We've got P, we've got Q, we've got R.
Yes.
Yes. Okay.
It is all true, yeah. And you says
okay.
P or
Let
Q.
me write that down. I'm going to put a T for each one of them.
Yeah.
Okay.
And that's P or Q is true, and it makes P or Q is true, yeah.
Yeah.
And it's not R. Is I'm talking about the pattern that you says that it's here is true and R is false, yeah.
Yeah. So if R is true,
yeah,
then not R is false.
I like the way in here that's not R or Q is it's all the pattern goes like true or false in that not R. It happens.
So not R is false, and then when I do not R or Q, okay.
Yes.
That's a false thing or a true thing.
Yeah.
So when you say false or true, that's true.
Yes. Yeah.
Now you can't see what I'm writing, but
oh yeah, no.
yeah,
I can see. Yeah.
Yeah.
True or false? Yeah.
Yeah, because not R is false.
Yeah.
You know. So
and Q is true already here. Yeah.
Yeah.
Yeah. Now I got the idea. Yes.
Yeah.
Thank you.
You are welcome. I'm looking for hands. Okay, I'm going to clear all the comment things because I don't know what's left over from the past. And then let's do the raise your hand if you got a question. Okay. Okay, well, that's looking hopeful. Let's see. Go on to the next page. Well, this is, in a way, it's redundant. See, they wrote the whole expression up top here, and then they're just filling in values for the variables and their negations. They're not like doing all this the and the not and or, the or and the not and the and, all the logic symbols here and the grouping symbols, they're not doing them yet. They're just writing the values for the variables or their negations. And then what they do in the next step is they say, okay, the next thing I'm going to have to do inside the innermost parentheses is this and right here. So they make a column where they fill in the and. And then they say, well, the next thing that comes after that is the not. So they're knotting the and. See, so because the and was false, then the not over here gets to be true. And in the next row, see where the and is true, then the not over here turns into false. And so they filled in first this column and then used it to fill in this column. And now they, in column 5 here, they have the whole square parenthesis done. So they've got the P out front, they've got the or, and then they've got the value of the whole square parenthesis. So when it's true or true, that's true. True or false, that's true. False or true, it's still true. So it came out to be true all the way down. And so if you find it's easier this way, less writing, you can do it this way. Or if you prefer to make a lot of columns, like where you just keep adding columns one by one, you can do it like the previous example back here, whichever you're more comfortable with. Or you can do the thing that I did. Where am I? Where I just kind of evaluated the expression like I was substituting numbers into an algebraic expression in the algebra of the number system rather than the algebra of logic. Okay, so, a student asked in the chat, how can you tell if it's a statement or not? And so a statement, it has a definite truth value. It's either true or false. You don't have to know already whether it's true or false. It's just the kind of thing that you could say that, well, if you knew, it would have to go one way or the other. And it wouldn't be a matter of opinion. It would sort of have to go the same way. Well, where you could at least define things. If you just define things well enough, then it goes one way or the other for everybody. You know, so like if I say, it is raining outside, I mean, I would call that a statement. And you say, well, people might have opinions and whatnot, but I guess what I'm saying is, in principle, you could pin that definition down to the point where there would no longer be a debate about it. You might not know for sure, but that's not relevant. It's that it is one way or the other. Yeah, some of them, It's like some of them, if you analyze too deep, you can decide maybe you can create issues where there's not supposed to be an issue, you know. But what's not a statement, you know, I'll give you one that's clearly not a statement would be something like, go to the mall. Okay, don't. We've got a pandemic, but don't go to the mall. It's not a statement. It's not true or false, right? Okay, or so a question or a command would not be a statement. And a thing that's really opinion, you know, where even in principle, there's no way to get a real objective answer to it. Okay, so that would not be a statement if it's just an opinion. And that's where it gets hard to decide, because is it where there is an objective answer, but I just don't know it, and maybe neither does anybody else? That could still be a statement, you know. You'd say, there is life on Mars. I don't know. I don't think anybody else knows right now. Okay. But it's still a statement, you know. It's one or the other. But, you know, something more not very well defined, you know, would not be a statement. To the student who was asking, you can put it in the chat again if you want to, or you can talk about it with me. I mean, does that kind of do it? Kind of, there's some kind of statements that are like, kind of, yeah. I mean, there's some statements like, you say, this sentence is false. That's not a statement. The grammar makes it look like a statement, but if it's true, then it's false. If it's false, then it's true. It can't be either one. And so it's not a statement because it can't be either true or false. So that's it. It's something where if only we knew, it's got to go one way or the other. That's a statement. Where it's a command, a question, an opinion, or nonsense, those don't count. Well, that's about all I can say about it. Yeah. Okay. Yeah. You can, yeah, it's great that we have YouTube now too, because you can search for, you know, what is a statement in logic, and there are probably, you know, 30,000 teachers out there who have made their videos on what's a statement in logic at this point, so you can see how different people say it and different drawings that people make and so forth. And that's another approach. The problem with I've got a few ways I can say each thing, and then I'm going to run out. But maybe somebody else out there has got more, you know, more ways to say it. Okay. So let's see. Anybody else with questions on the truth tables? Okay, so we got our first method. We got this method I was just showing you here, different ways to organize it. The meaning's the same. And then there's this idea of equivalent statements. And I do have something I can write, I think, to help with this by making a comparison to what you already know from algebra with numbers. Okay, this first one, the x plus 5 equals 7, it's true if x equals 2 and false otherwise. Now, this other one over here, the commutative law of addition, it's true no matter what you put in for A and B. So you have the same kind of thing in logic. We've got P and true equals true. That's true if P equals T. Now I can say P equals T, but usually you don't do that in logic. You just say if P, if it's true, if it's raining. P stands for the words, it's raining. So true if P. Say if, I'll say P is true. The point is, like this equation up here is only true if x is a certain specific number. Down here, this logical expression is true, equals t, only if p has a certain value. The way we've set it up, you say, the way the book is doing the notation, I wouldn't say p equals t because they're saying p stands for the actual statement. P stands for like the words it is raining. So we wouldn't really write an equals there if we're doing it the way the book is thinking, where the P stands for some statement in the real world. Now, pure logician would say, now, P, it's just a variable. It's got two different values, T and F, and none of it refers to anything in the real world. Okay, so they would use equals. That's okay. So that's that. And over here, Same kind of thing, the commutative law for the conjunction, it's always true. And whatever you get on the left side, you'll get the same thing on the right side. So that's the idea of equivalence. So how do you use truth tables to show that two different expressions, like these two, are equivalent? So I can make a truth table for this first one. So here's the values for the overall expression, the blue column, column 4 in the left-hand table. And then I can go to this other one over here, and here are the values of it, the blue column, column 3 in the right-hand table. And I compare those two truth tables, and if the blue columns match all the way down, they're giving you the same values regardless what the inputs were. Doesn't matter whether P and Q are true or false. It's for all the different combinations, you get the same thing either way. That's what you mean by equivalent expressions. And so you can write this equals with 3 bars, not just 2 bar, not just equals, but really equals. And so that's how you check for equivalence. And you know, in algebra, when you do this game of simplifying expressions, what you're doing is you're saying, I don't know what the variables are, but I can make another expression that will have just the same value regardless. You know, so if I write if I write 2 times x plus 2, that doesn't just equal 2x plus 4 by the distributive property. It's not just equal, it's equivalent. When I teach algebra, I see students get confused between whether they're solving an equation or simplifying. See here, there's nothing to solve. I can't try to figure out what x is. I'm just saying you can replace the one thing with the other, whatever x might be. I simplified. I didn't solve anything. Okay. So when I simplify x plus 2 squared, I'm not going to find x. How would I find it? X could be any number. It could still be, you know, doesn't matter what kind of algebra I do, it could still, x could be anything there. That's simplify. There's nothing to solve. Okay, but there's solve. And it's the difference between the 3-bar equal, the equivalent of expressions versus just equality. Okay. So much of learning algebra was learning rules for which kind of expressions are equivalent and which are not. And fortunately, there's only like 8 rules, you know, commutative and associative properties of addition and subtraction and multiplication and division, and then you have the distributive property. Okay. And so I used this one earlier today when I simplified that expression back at the beginning. We were doing this truth table, and I did this thing. See, they're not just equal, those are equivalent expressions. And I showed they're the same by showing you get the same truth table. And that's the check your progress 4 over here in the textbook. Okay. How are we doing down to here? Let's look for another show of hands over here about the questions. Do you have questions about equivalence? Let's ask a yes, no in the participants window. Okay, I'm looking for just a poll, so I can get a rough idea of how many students there are. Do you feel okay about the 3-bar equal versus the 2-bar equal? Some yeses, some nos. Okay. I did get a no up there. I'm gonna talk about the example with numbers for just a minute. It's great if you want to turn on your microphone and talk with me about it as we go along. If you don't, that's okay too. 5 plus 7 equals 2. Equals 5 plus, oh boy, x plus 5 equals 7. It's true if x is 2, but if you put in any other different number, it's not true anymore. It's an equation you could solve to figure out, okay, which value of x would make it true. That's an equation. But this over here is a statement of equivalence. It doesn't matter what 2 numbers you take. 3 plus 5 is the same as 5 plus 3, or any other 2 numbers. Those 2 expressions, a plus b, b plus a, always the same. That's equivalence. Okay. So the same way with the truth tables, or with logical expressions, here they're giving us 2 different logical expressions. We want to find out if they're equivalent. How do you show that they're the same with the truth table? You say, well, see, all the different combinations make it come out the same. But then once we know that, then whenever we see that pattern, okay, whenever we see the pattern, we can just apply it. And so we can replace a complicated expression with one that's not so complicated, but carries the same value. Okay. So like here's two of the most useful ones, De Morgan's laws for statements. We saw De Morgan's laws for intersections and unions of sets, and not surprisingly, it works the same way for logical statements. So it's not true that I graduated or got a job. That's P is I graduated, Q is I got a job. The overall expression is the negation of P or Q. Well, if you wanted to replace that with the conjunction of the negations, you have not P and not Q. It's the same, going to have the same value. You say, why would I want to? Well, it's the same question as in algebra. You know, why would I want to use the distributive law? Because sometimes I can make the overall expression simpler. Okay. So tautologies and self-contradictions, it's a tautology is a statement that's always true. Okay. So this, it doesn't matter, this example 6 here, no matter what you put in there, you always get true. You can show it by making the table. At the end, this blue column 5 has only true values as the entry for the final result. That's a statement that's always true. That's called a tautology. And then a self-contradiction would be a statement that's always false. See, like if you look at this one, they're going to get you to make a table to show that it's always false, but you can also just use verbal reasoning. For the parentheses part to be true, not P has to be true. The only way that parentheses is going to come out true is if P is false. So for the overall expression, you got to have P and also not P, both. You can't have it. So that one's always false. You can do the verbal reasoning or you can make the truth table. Nice thing about the truth table is you can find out whether you got tangled up in your verbal reasoning. Take the time to make the table or let a machine make the table, you'll always get it right. Questions up to here? Okay. So then you get your exercises, and that's all for section 3.2. There's an excursion. There's more switching networks. So in this one, I think we're going to simplify a few or figure out whether there's two different switching networks are equivalent. Anyway, it doesn't use new information. It just uses the tables to analyze the figures, and then you can answer some questions about the figures, about equivalence or. Okay, I think that's a good place to stop. I'm going to turn off the recording, wait just a few minutes to see if you guys have questions you want to ask after the recording's off, and then we'll call it a day.